Hello, everyone. I'm Haoyu Ji from Harbin Institute of Technology, Shenzhen. I'm glad to take a few minutes to introduce my paper LaDy, Lagrangian-Dynamic Informed Network for Skeleton-based Action Segmentation via Spatial-Temporal Modulation. Skeleton-based Temporal Action Segmentation aims to parse continuous skeletal sequences into frame-level actions. Current methods rely on deep architectures to capture these dependencies, using GCNs for spatial body structure and TCNs or transformers for temporal modeling. These models are highly successful at learning complex kinematic patterns, effectively capturing the what and how of human motion. However, current methods focus almost exclusively on kinematics, ignoring the physical forces that govern human motion. This dynamics-agnostic approach discards vital information about intent and causality, leading to two major challenges. First, it compromises class discriminability, making it hard to distinguish actions with similar poses but different physical intents, like walking versus moving a cart. Second, it hinders precise boundary localization because it blurs the abrupt force changes that truly define action transitions. To bridge this kinematics-dynamics gap, we introduced the Lagrangian-Dynamic Informed Network, abbreviated as LaDy, which integrates the principles of Lagrangian dynamics directly into action segmentation. Instead of solely observing how a person moves, LaDy reasons about why they move. It utilizes the Lagrangian dynamic synthesis module to explicitly estimate the generalized forces driving the skeletal system, guarantees physical coherence via an energy consistency loss, and leverages a spatio-temporal modulation mechanism to inject these dynamics into the backbone. Therefore, the contributions of our paper are threefold. First, we propose LaDy, the first framework to introduce Lagrangian dynamics into STAS. Its core is the Lagrangian dynamics synthesis module, which estimates physics-informed generalized forces to assist segmentation. Second, we introduce an energy consistency loss, a physics-based regularizer that enforces the work-energy theorem to ensure the physical coherence of the forces. Finally, we design a dynamics-driven spatio-temporal modulation that leverages these forces via spatial fusion and hierarchical temporal gating, enhancing action discriminability and boundary localization. Additionally, our method significantly outperforms existing approaches, achieving state-of-the-art results. Next, I will detail the methodology of our paper. As illustrated in the figure, this is the overview of the LaDy framework. The Lagrangian dynamic model on the lower left synthesizes generalized forces from coordinates, constrained by an energy consistency loss for physical coherence. Concurrently, the spatial model on the upper left extracts kinematic features using GCNs and fuses them with these physics-aware dynamics. Finally, the multi-stage temporal model on the right processes the fused spatial representation, where each stage is hierarchically gated by force-driven signals to enhance boundary awareness. To move beyond black box estimation, we first formulate the skeleton as an open kinematic chain to establish our generalized coordinates. We compute the root orientation via Gram-Schmidt orthogonalization and extract local joint rotations using axis angle representations. By applying finite differences to these coordinates, we derive the velocity and acceleration, forming the complete state variables for our dynamic system. Given these state variables, we estimate the four key components of the Lagrangian dynamics: the inertia matrix M, the Coriolis matrix C, the gravity vector G, and non-conservative forces F. Our core innovation is structurally embedding physical laws into the neural networks. For instance, we guarantee the inertia matrix is positive definite via Cholesky decomposition, and we ensure the passivity property of the Coriolis matrix by mathematically enforcing skew symmetry. Finally, by assembling these four terms, the synthesized generalized force strictly obeys Lagrangian mechanics. To regularize our force synthesis, we introduce the energy consistency loss, grounded in the classic work-energy theorem. As shown on the slide, we independently calculate two branches. On the left, the change in kinetic energy driven by the inertia matrix, and on the right, the work done by the net force using the trapezoidal rule. Instead of a naive L1 loss, we merge these two branches to design a scale-invariant relative energy residual RE, which is robust to varying motion scales. Ultimately, this physics-based regularizer guarantees that all our network-estimated dynamic components are self-consistent and strictly obey energy conservation. Next, we introduce the Spatio-Temporal Modulation module. The core idea here is to inject causal dynamic insights into our network to resolve visual ambiguities. As illustrated on the slide, the dynamic features, highlighted in yellow in our main diagram, are fed into two streams. On the left, spatial modulation directly fuses force data with geometric pose, enhancing the spatial representation. On the right, temporal modulation extracts three physical signals: power, torque, and torque change. These signals hierarchically gate the temporal feature flow. By doing this, the network becomes highly sensitive to high-energy events and abrupt dynamic shifts, which are key indicators of action boundaries. Next, let's move on to the experiments. We evaluated LaDy on 6 public datasets: MCFS 22, MCFS 130, PKU-MMD, LARA, and TCG 15. To measure performance, we used 5 standard evaluation metrics: frame-wise accuracy, segmental edit score, and segmental F1 scores at IOU thresholds of 10%, 25%, and 50%. First, let's look at the quantitative comparison. Quantitatively, LaDy achieves SOTA on all 6 benchmarks, notably surpassing prior bests by up to 5.2% on PKU-MMD v2. We maintain high efficiency with only 1.83 million parameters, validating our superior accuracy-efficiency trade-off. Qualitatively, LaDy yields more accurate segmentation with fewer errors. Crucially, our confidence curves show significantly less internal noise, producing sharper peaks that align precisely with true action boundaries, proving superior temporal localization. Finally, TSNE visualization reveals much tighter clustering and clearer interclass separation for LaDy. Quantitative clustering metrics confirm this, with our method achieving top scores across all indicators, validating a highly discriminative feature space. Here is our ablation study on the PKU-MMD dataset. Adding our Lagrangian-Dynamic Synthesis and Spatio-Temporal Modulation significantly outperforms the strong baseline. Finally, enforcing the energy consistency loss ensures physical plausibility, pushing our full model LaDy to the peak accuracy of 76.2%. To interpret what our model learns, we visualized the synthesized forces using skeletal limb thickness. As shown, the learned dynamics are highly intuitive. For example, hopping heavily activates the legs, while clapping focuses on the hands. This proves we successfully capture physically meaningful dynamics. Finally, analyzing our temporal gating signals reveals a fascinating phenomenon. Sharp valleys in the signals, especially torque change, precisely align with ground truth action boundaries. This shows our model effectively uses abrupt physical shifts to accurately localize action transitions. In conclusion, our proposed LaDy network effectively addresses the dynamics-agnostic nature of existing skeleton-based methods. By synthesizing physically coherent dynamics and leveraging spatio-temporal modulation, LaDy significantly enhances action discriminability and precise boundary localization. Achieving state-of-the-art performance across 6 extensive benchmarks and confirmed by physical interpretability, our approach successfully establishes integrating physical dynamics as a robust and precise foundation for future STAS research. Thank you for your attention. That concludes my presentation.